All right.
Well, welcome to the databases track here at the Erlang Factory. My name is Scott Listic-Ritchie. I'm at Basho. I'll be the track host for the entire day. Welcome. Really excited about this. I've sort of in the database business, the weird database business, and so the weird non-SQL-ish kind of stuff. Anyhow, so some of you may be relatively new to Erlang and wondering why you would do database stuff in Erlang, and you'll get plenty of answers throughout the day today. Our first speaker is Enrique Paz, and I should let him have as much time as possible to talk about his work. Thanks.
Okay, thank you. Thank you everybody for coming. So, okay, let's unblock this thing first. Otherwise, yeah, there we go. So let me start by introducing myself. My name is Enrique. I work as a senior Erlang developer for Spilgames, and I'm very enthusiastic about Erlang programming. I started with that several years ago. I really enjoy it a lot. To say something personal, something that I really like is reading other people's code. I like beautiful code, and I think, I find fascinating the amount of stuff you can learn about someone just by reading code. I work for Spilgames, and Spilgames is a company in the gaming industry, a company from the Netherlands. We're mainly a game publisher, which means we enable our platforms to distribute games developed by others, but we're also game developers as well. We serve data to more than 190 countries, allowing games. When I started working for Spilgames, this was something that amazed me. I mean, receiving connections from countries that, I did not know how to put in a map, to be honest. And we are more than 300 employees, mainly in the Netherlands. We have the headquarters in Hilversum. We also have a game studio in China. We serve more than 200 million unique users a month, and this is the actual challenge for us. What we do hosting the games is not really rocket science, but the volume is critical. And we make our money out of advertising and also end-user monetization. So here you can see a couple of pictures of our portals. We have portals for different target audiences. For families, that's for girls, a couple of games. First one is an in-house developed game, Sarah's Cooking Class, very famous, very successful so far. Second one is not one of our games, it's an external game, Galaxy Life, very nice strategy game, multiplayer. But I'm here to talk to you about storage platform. So, yeah, the first reaction that normally I find when I tell people in the Erlang world, well, we're developing our storage platform, is sort of like, what? Another one? Don't you have enough of that? Well, let me explain you a little bit on the reasoning behind. So, Spilgames as a company comes from a scenario sort of like this. This is familiar probably for most of you. Classical LAMP stack with MySQL. So our customers would enter our HTTP interface through a load balancer. They would be derived to a PHP application that would receive the code over there, actually detect what to do with it, maybe go to some cache, retrieve some data, then talk to another service with parts of that data that has recovered, build some more information for the request. That other service might need to go to storage, retrieve something from the storage, take it back, return to the first one. If you're lucky, not go to the third one, and then finally return an answer. Okay, and this is a very, very simplified version. I'm not talking about the caching proxies, the CDNs, everything. This is a mess. It works. It made us grow incredibly in the last 5 years, but it's really difficult to maintain, and it's really difficult to predict. Every time you change one of these guys, since these guys are talking to a lot of other guys and also talking to the cache and also talking to the storage, is really difficult. So main concerns. Your storage model is all over the place. Each one of these guys knows a little bit of the storage and a little bit of the cache. Since all of them are talking to the databases using native drivers, it's actually quite difficult to shard the data. Of course, not all your application developers are or should be DB experts. So you have a lot of performance concerns, security concerns. Yeah, and again, caching here I represented like one big shared cache, which is true-ish. But again, caching proxies, CDNs, everything is cached in many places just for performance. You have a lot of information cached on the client as well. It's difficult. So we really needed something different. And this is more or less the idea that we came up with. So what we would really like is the load balancer to address a request to a public interface that is very strictly defined and acts as an aggregator. And that public interface just aggregates information from the different applications. So these guys don't talk to each other. And each one of these applications, mainly Erlang now, also some Python, mostly for the monitoring tools, goes to this thing we call SSP. SSP stands for Spilgames Storage Platform. And this is the thing that we were trying to build beginning last year. So it's like, OK, what we really want from it is that the clients don't see anything about the storage at that point. They just ask the storage platform, give me this type of data. And I don't care where it is. I don't know what technology is used. And I don't care, to be honest. I just want the data. And of course, the platform should take care of the caching as well. Because again, the client application doesn't care if the application is, the information is coming from a cache or from a disk. And of course, lots of engineers talking, we always come up with very beautiful ideas. So it's like, OK, let's create a wish list. What type of things do we really want from this abstraction layer over here? Well, we want to make it a transparent sharding layer. We want to be able to shard the data based on the data ownership. So if we have data that belongs to users, we want to be able to shard based on user ID, for example. Of course, the platform should be highly available. It should centralize all the caching. So it should be good enough, performant enough, so all the caching is there, and we no longer need to spread our cache all over the flow. We want to have one and only one data model defined in one place, and not, as before, several applications knowing bits and pieces of the data model. Very interesting one. We want to be able to change the storage in a completely transparent way for the client, because again, the client doesn't really care how we store our data. So if we decide to switch from a MySQL table to a Swift storage for some type of information, the client shouldn't be rebuilt or modified or adapted for that. The client is just requesting data. And we want to be able to scale geographically, meaning bringing the data closer to the user. And I will get back to that later in the talk. So this is our big wish list. Now, in order to do that, to make it real, we want to have a clear mindset. And the platform, again, has to be always available. So we really need to distribute it and make it nice, make it work. We want to avoid global locks. Because in most classical storage engines, those are the real problem, and not only in storage engines. If you have any system using locks, if you lock globally, your chances of designing something that doesn't really perform according to your locks are really high. So we want to avoid them completely. And accept the change as the only constant and embrace the possible inconsistencies. Meaning your requirements are always going to change, your hardware is always going to break down. When you perform an upgrade, your states between the different servers will be inconsistent. You have to prepare your software to live with that. And of course, we were thinking a lot about the Dynamo paper from Amazon while looking at this list, and eBay architectural design principles. Lots of things. Also, already built systems for storage like RIAK, we were looking at the components that make RIAK possible and how it handles different things. We basically took a lot of inspiration, and we came up with an idea. It's, OK, let's build a key value store with schema. And it's like, what? Key value store with schema? Well, we liked a lot the properties of a key value store, the fact that you just have a key and retrieve a bunch of data, and it makes it easy to distribute and do a lot of things. But we also liked our schema, because it's easy for validations, basically. And this way, we can actually have the schema in the platform, and that's the only place where we have the schema. And since the clients are only requesting by key, they don't really need to know that schema in detail strictly. So it could just work. So the main components for this system are buckets, and this is a very similar concept that you can find in RIAK. Just, we generate the buckets from the definition. They're mostly generated OTP applications. And each bucket offers a CRUD-like interface where you can actually filter. For example, if you have a bucket for user high scores, you can actually give me all the high scores for this user ID, and there you have your key value store. But you can apply filters later, like that are more recent than last week. Okay. We have GIDs, or global identifiers, and this is 64 bits integers. This is what we use as keys. And they represent the data ownership. So in our company, at the moment, we have GIDs, meaning user IDs, and game IDs. Those are the two types of data owners that we have. And then the interesting bit comes in. This is, again, not a storage engine, but a storage platform that acts as an abstraction. So buckets can use different storage engines. So you can have a bucket for user preferences that uses just MySQL, if you want, a couple of tables there, and does all the combination. All the magic is hidden inside the platform. You can have a bucket that uses just a Swift binary storage. You can have a bucket that combines them all, basically. You can have a bucket with RIAK. You can have whatever you want. Okay? The storage engine is abstracted on top. And the platform is responsible for caching bucket GID combinations. So again, user high scores for some user ID can be cached. And the request can be atomic per bucket GID if needed. Yeah. And please keep in mind that we wanted to avoid using global logs. So this was a hard one. So how to operate with such a system? We have the components in mind. Now, what type of operations are we allowing our clients to do? Well, we have optimistic operations, and optimistic operations mean happy flow. It means like, OK, I want to execute something, but I really care a lot about speed. If something crashes, something goes wrong, well, I can afford it. I mean, this is not critical information. I just want it to happen fast. And this type of operations, of course, will update first the cache and then the disk, because you just care about having the data updated quickly. Consistency is not a priority in this case. You can afford a couple of crashes. For example, I mean, think about users' activity feeds where you track what the user has been doing. You don't really want to block your system waiting to update the activity feed for the user just in case a friend of the guy just immediately comes to the system and wants to check to the exact second what the guy was doing 1 second ago. I mean, if you miss one update, it's not that bad. Okay? And the same thing for the popular games list. Think about every time you start a gameplay, you really need to register one more gameplay. Well, if you miss one, it's not critical. Okay? There's one important thing that I want to remark here. There's no warranty of eventual consistency. Okay? RIAK has a very nice definition of eventual consistency with the gossiping protocol and stuff. We don't have such a thing. Okay? This is data that you can afford to lose, and that's the reason that you are operating optimistic. If you cannot, then you operate pessimistic. And pessimistic is the classic operation where you have all your warranties. So the consistency is the key. It might take slow, but you're going to wait for confirmation. If you receive an error message, something like that, you can retry your operation. you're dealing with critical data here. Think about payments data or personal user information. And of course, in this case, what you want is persist the data on the storage. And once that has been successful, then you update the cache, return to the client. The job is done. Yeah. All right. So how do you manage to put those components together and allow those types of operations? These are more or less the details. Again, you can find some familiar things from RIAK here. So the system in the different nodes, all the nodes will be running a lookup application. And that lookup application will keep track of a replicated hashing ring. Yep. And of course, a hash space is your GID space, so your key space. Now, the bucket applications will be started in the nodes. Nodes don't have to run all the buckets all the time. That's not necessary. You can have some nodes running some buckets and some others with others. Right? But when a bucket starts, it registers components, which we call pipeline factories. And pipeline factories, you can think about them as job managers, or something like that. Okay? Are they responsible for a range of GIDs to be operated successfully? And when the bucket application starts, it just goes and registers the pipeline factories into the hashing ring. So if you get a hash, let's say 1, then it would be managed by pipeline factory number 1, which is in node 1. Yep. OK, and the hashing ring we implemented as an issue table. It's replicated. We use RAM copies, dirty reads. Reading is, of course, the most common operation. Every time you have a request, you have to perform a quick read. And you only use a lock for the transactional writes. Yeah. All right. So in a pessimistic operation, destructive operation, the way the system works is the following. Any random node in the system, in this case the first one, receives in the bucket 1 request. It will try to look up the pipeline factory through the lookup application, the pipeline factory that is responsible for the GID. It will come up in this case with pipeline factory number 4. Pipeline factory number 4 will encode the job in a generic way. So it transforms your API request for profiles, insert, whatever, into a generic job. That generic job, well, first the factory ensures there is a pipeline, which is the actual worker for that GID. Yeah. It makes sure, well, either retrieves the one that's existing or creates a new one. And it queues that generic operation into this worker for the GID. And yes, I said we're queuing operations for 1 GID. And again, normally, when you rehearse this, you get some reactions from people. And this is what we normally get. It's like, you said what? You're queuing for 1 GID? I mean, that means you're creating long queues of operations? I mean, for what reason? Can you spawn processes? I mean, can't you do it any other way? And yeah, I mean, the criticism has a point. There's an issue with this. Sequential access for hotspots has a huge penalty. Think, for example, you have a very popular game where you have thousands of gameplays in a second. And all those requests are actually going for retrieving the basic game data, name, description, and stuff for the same game ID. And are we queuing all of that? I mean, that would be really bad. And yeah, indeed, it would be really bad. We're not doing it because there's a very simple optimization. I mean, you read from the cache outside of the pipeline. Now, how many pessimistic, destructive operations you get for the same GID in the second, well, that's not that a high volume as you can get for the reads. So you can manage that. And there are other pros about serializing this thing, which are, well, you don't need your storage engine to support global logs. So there we are. We avoided it. Why? Because we are just making sure one operation finishes after the next one gets executed. And this one also allows us to combine several storage engines for the same bucket, meaning that you can indeed combine SQL tables with Postgres tables, with Swift storage, with something else, whatever you want, and build your thing. And you're operating all those ones for the same GID. And until you're done, the next job cannot actually modify the information in those places. And of course, there's one more argument that is very explicit. That is, most of our GIDs are user GIDs. And users are always evenly distributed. I mean, you will not have the user that for himself executes 100,000 operations, pessimistic, destructive operations in 1 second. I mean, if you have such a thing, that's an attack. That's not a real user. Yeah? OK. In the wish list, we also wanted to, well, we also mentioned that we desired to be able to change this storage map, this thing about the several tables of different things, in a completely transparent manner to the client. And this is the concept that we have of schema versions. Yeah? This is not code version, this is a different thing, schema version. So schema versions determine what operations are allowed and what's the exact storage map for those operations. Client is never aware of them. Client will just issue a request and to retrieve some data or modify some data, completely agnostic on the version and on the real storage. And the system allows you to have 2 schema versions for a bucket running at the same time. And each bucket GID combination is running 1 schema version. This means when you decide to migrate the schema, you don't have to migrate it for the whole bucket. You just migrate 1 GID at a time, yeah, or a range. And a very interesting thing about this is that you can actually do it under heavy load, even, because guess what? The migration of schema gets queued in the pipeline. We also have a concept of shards. And we wanted the system to be a transparent sharding layer. And I'm not talking about SQL sharding strictly here. This is just generic sharding. So some of your GIDs for this bucket are in this cluster over there, and some other bunch is in that cluster over there, basically. And the system takes care of it. Yeah? It's, of course, useful for partitioning big blocks of data. And the sharding rules can be defined per bucket. By default, you can do something very generic, like GID module the number of shards. And of course, bucket GID combinations can be migrated between shards. And again, you can do that under heavy load. Yep. That means you can actually have control on where your data is. That's something that I mentioned before. Yeah. So how does this thing work? Well, let's zoom a little bit into what the pipeline does. So when it receives a generic job from the pipeline factory, what it does is, OK, for each job that it receives, it goes to the bucket. And the bucket application will contact these versions and shards thing, which is outside of the node itself. It's shared by the nodes as well. Yeah. And it's used to determine the version and the shard for that bucket GID combination. So once that thing is retrieved, the bucket knows, OK, I'm working with a GID that is in version 2, and it's actually stored in the shard number 1. So it goes to the specific code for the version 2 to build the details of the operation. Meaning, if this is version 2, I know this is 1 SQL table and 1 Swift storage. So this is how I build an insert. Yeah? So it creates a closure, something that it can actually be executed and modify the storage. This also gives you the advantage that you can put any type of logic in your specific mapping. So you can have, I don't know, commits and rollbacks if you want for your bucket. And they are hidden in here in the code for the specific version that uses that type of storage. You just implement it yourself. Yeah? And of course, there are some storage engines that will be more helpful for some cases and some others that will be more helpful for some others. So once the operation is exactly built, the pipeline has something to queue and just queue it. Basically, it's just a closure that is queued and built and run. And then it goes to the next one. OK, so this was a lot of technical explanation, but this is also one thing that we get a lot. It's like, yeah, sure. You mentioned a lot of things, versions, shards, different storages. But that probably means I need to know really a lot of APIs and a lot of stuff in order to use this system. And I really don't care what you do. I don't care about pipelines. I don't care about anything. I just want to give you a very simple operation in a very generic manner. I know no Erlang at all. And I want to be able to do it, to use your magical storage. So how can I do that? Well, for that, we use Piki. And Piki is an open source project. It's very nice. We use it a lot. Currently collaborate with Anton, who's the developer of Piki. I strongly recommend that you check it out. Basically, with Piki, we can define our schemas in one place and generate a lot of code out of it. We can generate the Erlang equivalents for that definition. We can generate automatic translators from those equivalents to protocol buffers, to JSON, and it also provides us with an HTTP server listening to it, which is based on web machine. So it's a lot of code. It's out of the blue. We don't write, and it just works. And so to talk with our system, you can just easily use HTTP plus JSON, or HTTP plus protocol buffers, or, well, OK, you know Erlang, so you want to do it performant manner. You just include that definition that I mentioned before in your client and use protocol buffers to encode the payload. And why the protocol buffers to encode the payload? This is because something that I mentioned before as well. There can be states mismatches between your cluster, right? So when you update that definition for your buckets, you don't update it in all your servers at the same time. I mean, that's delusional. It will never happen. So it might be the case that your client is using an old version of the definition or a newer one than the storage is actually using. So for that, you use protocol buffers to encode the payload. You could use a prop list. It just works the same way, basically. We use protocol buffers because it's more efficient. That's it. And you just encode and decode when making the call and when receiving the results. And as long as you use some common sense when modifying, basically, and you don't create mandatory fields out of the blue or remove fields from one version to the next, you just create optional stuff and make stuff optional, then it always works. Yep. All right. We also wanted to go worldwide with this. So in our vision, we differentiate two types of things, the pink data centers and the blue data centers, meaning master and satellite data centers. So the master data centers are the classic concept of data center out there, basically. It's this big, expensive building with lots of security measures and big wires replicated and everything. Really expensive. And of course, they have a persistent storage, and they can own GIDs. And with this, I mean each GID, well, bucket GID, will actually be owned only by one data center, which means it will be accessible only in one data center. This is a distribution layer, not a replication. The SSP doesn't take care of replication. This is distribution. And of course, you can migrate the GIDs between data centers, right? So classical case, I don't know, very simple one. You have a user that lives in Amsterdam, and suddenly you detect that for the latest 6 months, he has been accessing from Seattle. So every time you retrieve the data from the user, you are crossing the ocean, and it's really annoying. Okay? So you just migrate the data for the user to the proper place. You can also create your heuristics for the system to do that for you. Yeah? Because, of course, we don't have our DBAs just monitoring the users and migrate them manually. And the interesting bit here are the satellite data centers, because these ones don't have persistent storage. With this, I mean they are just a huge cache. That's what they are. And they are very easy to set up and decommission. We use them on the cloud, basically. So you can just easily use Amazon Cloud or Rackspace or something to just open a new satellite data center in an area if you want. So this is where you start. Basically, you have one data center, all the clients accessing via DNS to that master data center for all the traffic. You have everything there. You have a huge disk, security mechanisms, whatever, and you have a cache. But for us, this jump is very simple. Yeah? So this jump means you have your original thing, but also you open a satellite data center with its cache, and clients can access that one via DNS depending on where they are. Right? So we currently have one master data center in Amsterdam. Now imagine we have a lot of traffic from the States, which is not a lot of imagining. And we decide to create a satellite data center in the States to speed up this region. Yeah. So that we can just do by opening in the cloud, and then the clients will start requesting data. Of course, this data center will have absolutely nothing. So all the read operations and optimistic operations will not found the GADs on this cache. So they will have to go across the ocean, retrieve the information from the master data center, and get back. But once they get back, the information is cached. And then all the reads and all the optimistic operations will be executed locally. Yeah? And the beauty of this thing is that you didn't need to do any migration. You just rerouted the DNS traffic to your new data center. And suddenly, a huge cache starts to be populated, and you immediately realize that you are speeding up the process a lot. Yeah? And OK, you can do this because there is a big event, and you expect a huge peak in traffic, things about Olympic Games, this type of things. And then after 3 weeks, after a month, you're done. You don't expect that amount of traffic for the area. So you just close or decommission your satellite data center. It is that easy. But maybe, hopefully, that traffic increase is permanent. So you want to go and make it a master data center. And the only thing you have to do for this is, of course, find the appropriate place. And once you have the appropriate place, you just hook the disk in there and slowly start telling the system that now you're going to own this GAD that previously was owned by this other guy. Yeah. And again, you can use heuristics for population. All right. Very quickly over this, just to make clear the flow. This is the flow where the data center that receives the operation is the one that owns the GAD for the operation. And it's very simple. This operation is optimistic. You update the cache, and then you persist the data. And as soon as you receive the operation, you tell the client, yeah, whatever, I'll take care of it. And if it's pessimistic, you first persist the data on the disk with confirmation, then update the cache, and then reply to the client, it's done. If the data center that receives the operation is not the owner of the GAD, the flow is basically the same. But now there's one extra data center in the beginning. So if the operation was optimistic, you update the local cache. You tell the well, before even you just accept the operation. You tell the client, I will take care of it. You update your local cache, and then you create an operation that is exactly this operation. But you just package it, pack it in a wide area network operation type. That means we are also building a wide area network bus with replication and payload control and checksums and stuff to actually communicate between the data centers, right? And the pessimistic operations are just the same. Again, I don't own the GAD. I cannot do anything about the pessimistic. You have to wait. I will cross the ocean, do it in the proper place. But in the end, before returning to you, I will update my local cache. Yep. It's just the same flow. Yeah, this is very beautiful. But this is what normally happens with beautiful ideas. So what happens if we lose satellite data center? Well, basically, nothing happens. If you lose this, you're losing the speed ups in your area because your cache is gone, right? So the operations, well, as soon as you accept that you have really lost it and it's not like a temporary down or so, you just reroute the DNS to this guy and it's done. Yeah? Well, just reroute the DNS. And of course, you might be missing optimistic operations that were actually executed on this cache over here, but were on the way to be transmitted to the master data center, but then the thing exploded. So you have lost optimistic updates. But if you remember at the beginning of the presentation, you could afford losses in optimistic operations. So this is not really important. Now, this is a disaster scenario. Okay? If you lose a data center with a disk, this is pretty bad. Because it means that you might actually have, this data center owns GADs, so the information for these GADs is only accessible in this guy, and this guy is dead. Yeah. So even if you reroute the traffic and you realize pretty fast, a range of your GADs, the range that was owned by this data center, is no longer accessible, which is bad. And we also talked about critical data here. So does this mean that we lost critical data? Well, yes and no. Luckily, mostly no. The thing is, I mentioned it's not responsibility of the storage platform to take care of the replication, but I didn't say do not take care of the replication. Okay. So imagine this is very bucket dependent, but you can have an asynchronous replication mechanism going on, basically, in your flow at the system level. Imagine you're using buckets with a MySQL backend. You can use MySQL replication if you want. Or you can implement your own replication mechanisms, again, system level. This means, of course, that you are still losing information because this is asynchronous. So the latency of that connection will make you lose a couple of seconds of operations. And it's bad. But now compare that with losing a real data center. I mean, it's bad, but it's not that bad. All right, so let's wrap it up. What have we learned in the process and where we are at the moment? We're using simple buckets on live with one data center in Amsterdam. We have added a relap support for bucket-only updates. This means when you just create a new bucket or modify a bucket, you don't have to stop the nodes. You just load the code for the new bucket. Of course, if you update the core of the system, you will need a reboot. But doesn't mean that you have to reboot all the nodes at the same time again. We're hammering SSP with property-based testing for validating all the buckets interfaces and also for generating complex scenarios of lots of traffic doing pessimistic operations at the same time and nodes being shut at the same time, and see how the jobs are transferred from one pipeline to another. Everything is still working and it's consistent. We're integrating restricted search capabilities, which is something quite nice for a key value storage thing. We're testing the one protocol for the inter-data center communication, and we will have more buckets going live this first half of the year, and a couple of satellite data centers coming for the second half of the year. And in the process, we have used a lot of software. Of course, no one wants to reinvent the wheel all the time. So our old storage was MySQL, and we still use a lot of MySQL through eMySQL, which is a nice Erlang library. We have, well, the pluses here mean actual contributions that have been accepted in the upstream, and the stars are pull requests that we have issued to the owners of the repos. So we have contributed multi-database transactional support to eMySQL and multi-time zone support. Of course, we have used Jiffy and EEP for JSON encoding, decoding, eStatsD for hooking up graphite monitoring, which is really nice. Proper for the property-based testing so far. Poolboy as a worker pool for keeping the memcache connections, and Lagger for logging. Rebar as a building tool, really nice. Have contributed semantic versioning for it to improve the dependency versioning, and shared dependency system to speed up the process where you are on your development machine, and fixes for the XREF support. We use Picky, and we also modified a little bit Basho Bench to add support for deploying several graphs on the same picture, basically. So you can actually compare the lines in one go. The slides will probably be on SlideShare or so. So all these purple things and also the stars and the pluses are clickable. Feel free to go and take a look. That was it. So now it's time for you to ask questions.
Questions for Enrique
Yeah. I was thinking about doing that, and it's the clear slide that is missing here, you know, the numbers that everybody wants to see. But I didn't include them in the end. And the reasoning is the amounts of operation currently going through this platform are not relevant compared to the amount of operations that we are still handling in the old architecture, basically. And also, we have more and more backends going live, so probably we will make a slightly modified version of this talk in the Erlang user conference in June. And by then, we will have nice numbers. What I can tell you for now is that using Basher Bench and property-based testing to generate sequences and loads, shooting the system in parallel, the breakpoint was either MySQL or the client submitting the request, but never the software in the middle. Yeah, that's it. Yep.
How would you test this kind of system before actually putting it into production?
How do we do it?
Yeah, how do you do it? How do you test? How do you know how the system behaves under big load?
Yeah. Well, at the moment, we're mostly doing, well, of course, we write unit tests for the basic scenarios and the more complex one for the stuff related to a hashing ring and these type of things. But the interesting testing comes out of two flavors. The first one is input and output validation. And we do that with Proper, with very complex generators of input and output and checking for every operation that basically if the operation is valid, then I should have modified storage and an OK result. And if not, I shouldn't, basically. So it's very simple to say, but it's not very simple to test. We use Proper for it. And then for the load, and the interesting stuff, what we do is generate sequences. We use a Proper finite state machine. Quick Check has the same thing as well. And we basically generate sequences of operations, destructive operations, pessimistic ones, inserts for the same GID and these type of things, and then reads. And our only post condition is after a read, I know what I inserted last, basically. So that's what I should be seeing. And in the meantime, we do all type of nasty things, like flashing the cache, shutting one node, killing one node, and especially with the parallel sequence testing, it's very interesting because all those commands and all those nasty things are actually happening in parallel, and the sequence are interleaving. So, and actually Proper can shoot pretty fast, and I'm pretty sure Quick Check as well. And yeah, for more detailed load testing, we use Tsung. For the Tsung, or I don't know how to pronounce that. TSUNG.
Okay.
Yeah.
Thank you.
Yes.
You mentioned something that the storage also supports updating several elements at once.
Updating, yes.
And how does this work? Like, and then you describe the system that's based on hashing the key space.
Yes.
Right. So my question is, how do this work together? Do you need to specify several those GIDs that you want to update, or you support range operators?
No, maybe I explained myself wrong. Each operation, this is still a key value storage. So each operation you do affects only one bucket GID combination. You cannot do one operation that affects several GIDs, basically. That's not the design. The design is more key value storage-like. But a GID, a bucket GID combination can map to different type of storages down, and you're protected between different operations with a pipeline mechanism.
So if you're mapping it to a table,
yes.
Then you should do whatever you.
Yeah, exactly. The exact implementation of that schema version with that mapping knows that, okay, if I have to modify this SQL table in this Swift store, I will do the first one, then the second one, then check they worked. You can go as complex as you want there. There's specific logic for one bucket schema version. Yeah. Yes?
Well, first of all, congratulations, very nice talk.
Thank you.
My question is about monitoring.
Yeah.
You mentioned you have some applications in Python to monitor your system,
Mm-hmm.
but then you also mentioned
Yes?
So first, why Python and not everything on Erlang? And
Yeah.
secondly, how did you guys handle monitoring without affecting the performance of the system?
Okay. Most of the monitoring, we do it with Graphite. Graphite is a pretty nice tool. We hook into Graphite with eStatsD. This library by Richard Jones is a very simple library, very nice. And with that, we can measure how long typical operations takes, the hotspots, the amount of stuff, some lines of code are hit, and this type of things. And it's real-time-ish, so a couple of seconds delay. But it allows you to explore those graphs, has very nice history support. That's what we mainly use. Now, I mentioned Python because this system is fully built in Erlang. But of course, unfortunately, we cannot count with 100 or 200 Erlang developers in these 300 people that we have in the company. This means most of our DBAs know a lot of MySQL because that's where we come from, and we have huge volume in MySQL. But if they have to do something with this platform, they will not be able to do it in MySQL. It is, yeah, OK, so how do we do it? We cannot use PHP, MyAdmin, or whatever. So OK, what can you code? Well, we can code Python. OK, then you can code HTTP plus JSON. That's the thing. So we have Python applications for hosting operations and DBAs to be able to manage the migration of the GIDs and this type of thing the way they want. Does that answer your question?
Yeah.
Yep.
What about queries? You say you use filters.
Yes.
And how does it work? What kind of indexes is built?
Yeah. This
sorry to
yeah.
interrupt. The people have been asking in the chat room if you could repeat the question because it's easier to hear you, Enrique, than the people in the audience.
Oh, of course, yes. The question was, how do the filters work when you operate via the interface of a bucket? And yeah, the answer is the operations work, basically the pipeline operation retrieves or operates on a list, so everything, bucket GID combination access a list of Erlang records internally, okay? And then you apply the filters on that list to actual, with a fold, basically, or list comprehension or something like that. And that's how you do it. And also that means that when we cache the whole list of records. We don't cache filter results. So each bucket GID entry that is cached is either fully cached or non-cached at all, basically. And that's how you make it. And then in the filters, well, when you define your bucket API and the fields that you have in your schema, you also specify, we don't allow free filtering, like just write whatever you want. It's like, no. We specify a couple of filters that you can use per bucket. Yeah. OK, I'll be approachable later and also tomorrow. So any other thing that you want to ask, it will be my pleasure. And just allow me to mention, of course, big thanks to everybody. And we're actually hiring. So if someone is interested, just go and take a look.
Thank you, Speaker. Thank you.